In this episode, we had promised you a rundown on Barry's extreme Toyota KP60 Starlet rally car. You know, Barry, Brandon, Barry, the two first name guy. Anyway, that's going to have to wait because in the meantime, we had a bit of a spanner thrown in the works with our Toyota 86 race car. We're only 7 weeks away from the start of the South Island Endurance Series, and we found ourselves potentially without an engine, and it's not going to be very fast with no engine. Anyway, let's find out what our solution is. All right, we've got a few problems. Problem number one is this.
There's something missing, there's no engine.
Second problem, let's go have a look at our old engine.
So you may remember this engine from our previous vlogs, and we actually find the spot.
Yeah, that's really our other problem. It's got a big hole in it. Now, if you've been watching, you'll know that we are building a replacement engine. This is going to be a 4.5 litre engine based on the 3U ZFE. Next problem number 3, is that our pistons are still being machined by Ross over in the US. We're a little bit worried that there's not going to be enough time to get those pistons machined, freighted here. Our engine machinist is in the other island, the North Island of New Zealand, so getting the parts even back from our machinist is probably around about a week's time on the courier. We've then got to assemble the engine, get the engine into the car. We've got a solution though, and we love a challenge. Let's go check out the solution.
So you'll remember that we did start a project for our 350Z, which included building this SR20VE engine.
Last night, Ben had a brainwave. Why don't we just pull the engine out of the 350Z, bang that into the 86, job done, easy. We've got a built engine, it's ready to go. Now obviously things aren't quite that simple, but we do like a challenge, and we're going to at least pull the engine out of the 350 today, test fit it into the 86 and see where we sit. Now on face value you might be thinking, this is a ridiculous idea. You'd be right. However, there is a little bit of method in our madness. First of all, we've already got a bell housing and adapter for the TTI 6-speed sequential gearbox. What we're hoping is that we can leave the gearbox in the existing position, so we don't need to make a new drive shaft, we don't need to make a new gearbox mount. All of the linkages for the shifter will still line up. So that will fix one of our problems. We just need to remount the engine. The other aspect here is the SR20 should be good for around about 650 horsepower at the moment, much more power than we're going to get out of the 3U ZFE. This also drops us down a class, and this is because we're currently running in the 3.5 litre and above class. So we're completely outclassed. There's a couple of 650, 700 horsepower LS combinations. There's a turbocharged 2JZ making similar power. We're just never going to be able to make that sort of power out of our naturally aspirated 3U. However, going to a 2 litre turbo drops us down into the under 3.5 litre class. Here in New Zealand, there's a multiplication factor for turbocharging, 1.7 times the engine capacity. Anyway, that drops us down a class where we potentially should be reasonably competitive. Don't want to jinx us, but that's kind of the idea that we've got in the back of our mind. Obviously, there is a lot more work to do though to get this up and running in the following 7 weeks. We've got intercoolers to think about, we've got the rest of the cooling system for the radiator. We're also a little bit concerned about heat rejection. Obviously going to be producing a lot more heat with that turbocharger in and around the turbo exhaust manifold, etc. But let's see at least how our test fit goes on. That'll give us a bit of an idea whether we can even persevere with this. One of the sensors we're going to be adding onto our SR20 is a turbo speed sensor. These have been around for ages, but historically they've been a complete ball ache to fit because there's been no easy option of mounting them through the compressor cover. So you sort of had to get real technical on drilling through the compressor cover and having a way of fastening the sensor down and making sure that where you're drilling it through is coming through so it can actually see the blades of the compressor pass by. Obviously you need to seal that as well so it doesn't become an air leak. Fortunately, the turbo world has caught up with our need for more solid data. So these days, a lot of the mainstream turbo suppliers have compressor covers that are really fitted with a real easy way of adding that speed sensor. So let's have a quick look at our Garrett GT86 Gen 2.
So for a start, we've got our turbo speed sensor here. You just buy these direct from Garrett. Now, they do have this big black ugly connector on the end, and given that you can see there's two wires running to it, it can be tempting to just lop that off and terminate it in something a bit nicer, maybe a DTM connector. Don't do that. This has a conditioning circuit in it. If you cut that off, the thing is not going to work properly. Secondly, let's have a look at our compressor cover, and we can see we've got this little location here that comes with the compressor cover for that turbo speed sensor to fit. Nice and easy. It's already drilled in the correct orientation. It's already threaded, and if we flip this over, we've got a little hole coming through here, which is where the sensor is able to actually see the edge of our compressor wheel. So this straight away fixes that hard part of actually getting the sensor into the correct location. Basically all of the hard work is done for us. And Garrett also provides some pretty simple documentation on how to go about that. Obviously you want to make sure that the sensor isn't protruding too far, or you're going to end up carving a big gouge into your brand new expensive compressor wheel. Next obvious question is, what are we going to do with this data? Well, let's take a look at how that comes into play. Here we've got the compressor map for our Garrett GT86 Gen 2 Turbo, and if you've got even a passing interest in turbochargers, you've probably seen one of these before, but maybe you don't know exactly what they mean. So let's dive into it in a bit more detail. Starting with the vertical axis here, we've got our pressure ratio. Now, this isn't boost pressure, which a lot of people mistakenly believe. Instead, it is, as its name implies, the ratio of the pressure across the compressor wheel. What we want to do is take our compressor outlet pressure and divide that by our compressor inlet pressure. Let's put some numbers around that, and to keep the math real simple, let's assume we've got 250 kPa absolute pressure at the compressor outlet, and our inlet pressure at the compressor inlet is 100 kPa. Simply 250 divided by 100 gives us a pressure ratio of 2.5. It's also important when we're thinking about pressure ratio here to understand that the pressure at the compressor outlet could quite likely be different to what we're measuring in the inlet manifold, and that's normally where we take our boost pressure signal from. The reason for this is we're almost certainly going to have some amount of restriction and pressure drop through the intercooler plumbing and definitely across the intercooler core. So what this means is that if we are using boost pressure in the inlet manifold for our compressor outlet pressure, chances are that the pressure ratio the turbo is actually operating at will be slightly higher than what we're calculating. Let's have a look now back at our compressor map and see how that 2.5 pressure ratio value actually works out. So since we know that our pressure ratio is 2.5, this means that we're operating somewhere along this horizontal line here. There's a few more aspects that we want to touch on here. One of the key ones is the efficiency islands, which are these little oval shaped islands. The center one here we can see is listed at 76% efficiency. Now what these islands are telling us, no big surprise, is how efficiently the compressor is working depending on where we are operating on those efficiency islands. What we need to understand here is that when we compress air, naturally it's going to end up being heated up. But the more efficient the compressor is operating, the less additional heat is added into the air. So depending on where we are operating inside those efficiency islands really defines what the compressor outlet temperature is going to be. And we obviously want to be operating at as a higher efficiency as we can. This really comes down to our turbo sizing and compressor selection to suit our engine and our desired power outcomes. Let's have a look at a couple of other aspects now. Down the bottom of our compressor map, we can see we've got our corrected airflow in pounds per minute. So this is the airflow or mass airflow that the compressor is producing. And this is one of the key aspects with turbo sizing, because the rough rule of thumb says that we need approximately 10 pounds per minute of airflow for every 100 horsepower we want to make. What this means, for example, is that if we have a compressor that is able to support 60 pounds per minute of airflow, this means that we should be able to produce somewhere in the vicinity of about 600 horsepower. Now this is a rule of thumb, it's not absolute.
we may find that if we are running on a low octane pump fuel, we're a little bit more limited because we will end up with the engine suffering from knock and we can't optimize the spark timing to MBT. On a race fuel, we're obviously going to be able to make more power at the same boost level. So it is just a guide. However, the problem with our corrected airflow is that unless we've got a very accurately calibrated mass airflow sensor, it can be difficult to know exactly what that is. So we may not be able to get an exact fix on whereabouts on that axis we are operating. That is where our turbo speed sensor comes in. Let's have a look at our map again. So we can see that we've got these other lines that run through our compressor map here, and down the right hand side we've got these values. So these are our turbo speed values. So now let's say, for example, we're still operating at our pressure ratio of 2.5. Let's say that we are also measuring a turbo speed of 115,000 RPM. So now this gives us a fix. We know exactly whereabouts we are operating. And if we drop down to the bottom axis here, our x-axis, you can see that 115,000 RPM at a pressure ratio of 2.5, we're going to be operating somewhere around about 46 pounds per minute of airflow. So this allows us to know exactly where we are on this map. The other aspect with our turbo speed is that it allows us to make sure that we aren't overspeeding the turbo, or in other words, working it dangerously hard. Basically, every turbo is going to have a critical speed above which we can expect turbo failure. So monitoring this, particularly in applications where we are pushing the turbo very hard to its extremes, is a great way of making sure that we are going to retain reliability. This is a problem we see a lot, particularly at hill climbs such as Pikes Peak, where there are very large changes in barometric air pressure due to the very high altitude. And at Pikes Peak in particular, we see a lot of cars that have a turbo that's sized perfectly for operation at sea level, and as the car goes up the mountain, the barometric air pressure drops, which means that if we are maintaining a consistent manifold pressure, boost pressure in the inlet manifold, because the compressor inlet pressure is constantly dropping as we go up the mountain, the turbo is actually operating at a higher and higher pressure ratio. If we aren't monitoring this and we aren't monitoring our turbo speed, it is very easy to end up exceeding the maximum speed of the turbo and ending up with a failure. So there you go. Turbo speed is not an essential sensor by any stretch of the imagination, but it does really open up what we can do and how we can analyze the operation of our turbo. This is really important for events such as Pikes Peak, but it's also really valuable when you are comparing two turbos and seeing their relative operation and performance. Alright, 3 p.m. update on our SR20 conversion, and at the moment it's been a bit of a fact-finding mission, seeing whether or not it's actually going to be possible to do this engine conversion, and if it's going to be possible, what challenges exist. So let's dive into the engine bay and we'll have a quick look at what we're dealing with. Alright, so we've got the engine sitting in place, and one of the first things with any engine conversion is just checking the physical fitment of the engine. Obviously, if the engine isn't going to fit without major surgery, then that's going to be problematic. In our case, the two challenges we've got is the clearance between the sump as well as the front of the bell housing and our cross member, our anti-roll bar, as well as our steering rack. And then of course we've got the gearbox at the back. Now that TTI 6-speed sequential has already been in the car behind our 1UZFE. However, with that long bell housing we're using behind the SR20, this moves the gearbox about 250mm further back. That trans tunnel in the 8.6 is relatively narrow, so this is a little problematic. And what we also found is that the gearbox ends up needing to sit a little bit low. So I've got the whole thing, the whole engine and gearbox sort of sitting a little bit tail down at the moment, and that's something we're going to need to correct. Ideally, what we're going to want to do there is cut the top of the transmission tunnel to allow us to lift the gearbox up, and we're also going to be replacing the current Moroso wet sump with a dry sump system, and that's going to allow us to drop the front of the engine, so we're going to get it nice and horizontal. The other aspect that's a little hard to tell here, but take my word for it, we've got it pretty much as far back in the car as we possibly can. Now, this is important in a race car from a weight distribution perspective. The further back we can get that large mass of the engine, the the better. Obviously we want it as low down as possible. Again, as we've already discussed, the crossmember and the sump really become the limiting factors on that. This SR20 is actually quite a tall engine, and the engine bay in the 86 is relatively slim anyway, given that its factory form, it houses a horizontally opposed boxer, so it's not a very tall engine. So we've got some challenges there in clearance around the front of the rocker cover to the underside of the bonnet. Let's dive under the car, we'll get it up on the hoist and we'll have a look at that gearbox location. First of all, let's have a look at the way the gearbox is mounted. So this is the front section of the factory SR20 5-speed gearbox. So it's quite long because it actually includes part of the gearbox itself. So it's not just a bell housing. We've got this CNC machined adapter that TTI produce, and then we've got our 6-speed TTI sequential behind it. So as you can see, it is quite a long bell housing, and as I mentioned, moves this gearbox a long way rearward. So we can actually see this was the existing location for our gearbox crossmember, which now comes all the way back here. And while you can actually see that it's sitting with a bit of an angle, this is exaggerated at the moment, we can actually lift this up and it gets it a little bit closer to level. But if we come around here, excusing our current temporary gearbox mounting solution, obviously all just dummied in for the moment, you can see up the top we've got a limited amount of room before we're going to be hitting the top of that transmission tunnel. At the same time, if we come forward here, I was talking about the clearance to the subframe. So we've got our Moroso Sump. The sort of clearance to the crossmember actually isn't too bad. At the moment you can see we've just got a piece of square steel section that is just supporting it to make sure we've got some clearance. We will be dropping this down as I mentioned, so it's not going to be sitting that high. And you can see as well the other issue why we've got that box section in here, clearance to the anti-roll bar. Well, at the moment we haven't got any, and the steering rack as well. For our initial test fitting with the engine, we actually ended up removing the steering rack because of the lack of clearance there. So we're confident again with the dry sump that we're going to be able to get around that. Otherwise, maybe we'll have to resort to Bluetooth steering. I don't actually know if that technology's been created yet, so this in itself could be problematic. Maybe we can get Elon Musk onto the case. He's pretty smart. Come on, Elon, help us out. Back into the engine bay, the other consideration we've obviously got is making some new engine mounts. So we can get down here. This is the engine mount that was fabricated to suit our 350Z. And we can see all the way back here, that's the hole where the factory FA20 engine mounts go. So you can see we're probably 150 odd mil too far forward. The other issue though is that the dry sump pump is going to sit here. Now this is the Nissan power steer pump mounted on the side of the engine. We don't actually need this because the Toyota 86 runs an electric power steer rack, so we can get rid of this. This is where the dry sump pump's going to mount, and we obviously need to keep that in mind because clearance between the back of the pump and the engine mount is going to be critical. So as you can see, there's a few moving parts to this engine conversion. No one said it was going to be easy. There's a lot to consider, but at this point it looks that it's going to be at least possible, if not a hell of a lot of work. One of the changes we're making to the SR20 is to remove the existing Moroso winged and baffled lower sump, and we're going to be fitting a full proper dry sump system to it. Dry sump pretty much the way to go in just about any competition car to ensure reliable oil supply under heavy lateral G-forces from cornering, and then also braking and accelerating for that matter. Let's have a look at the existing sump now. Obviously we've got the engine upside down at the moment on our stand, so this is the Moroso component of the sump, and it actually bolts to the existing cast upper sump. It's upside down, so upper, lower, yeah, you get it. So it's baffled inside. We'll grab it off in a second and have a look at how that works, and it also, these wings on either side just give us a little bit more oil capacity. They've been pretty well proven. These designs have been around for a fair while from a bunch of different manufacturers, and they are pretty well proven, but probably good for a modified street car, not so much for a full competition car running on slicks. Anyway, let's get it off and we'll have a look inside it. Now we've got the sump off, we can see what's inside and how it works. There's nothing too complex going on here. We can see
see that we've got this little hinged trapdoor. I've got one of these on each side. And the idea behind this is that when the car corners, the oil can flow from the wing back into the center, so the trapdoor will easily open to allow the oil to flow in. And when the car corners the other way and the oil tries to slosh out into that wing, this closes and holds the oil down here around the oil pickup. So the idea is a constant supply of oil, obviously what the engine needs.
Now that we've got the lower sump component off, the next job is to remove the cast section of the sump. So let's get stuck into that. Little pro tip with the SR20, probably most people working on them already know about this, but if you're fresh to the SR20 and you are trying to remove a sump, don't forget the two little 10mm headed nuts that are at the back of the sump. Let's check those out.
These little guys here, turns out they're quite important if you want to be able to remove the sump without breaking it, so don't forget about those. If you are doing this with the engine still in the car, you can remove this little inspection plate and that'll allow you to awkwardly get through there with a ratchet ring spanner.
We're now at a point where we can remove that cast section of the sump, and this can be a real pain. It's generally going to be stuck on there pretty thoroughly with the sealant, and it can be quite hard to break that seal. There's a couple of options here, so I'll just talk you through those. Again, just helpful to have this in your bag of tricks. Let's have a look.
So the first option, which is what we're actually going to do, is we can get a big wide pry bar in here between the block and the cast section of sump. A little bit harder, but around on the other side we can also get in through here as well, and using a wide pry bar we can just gently lever that off and that'll break that seal and we won't be doing any damage to the block. Nissan in their infinite wisdom actually thought ahead though, and there are these threaded holes at the back of the sump. We've got one on this side, we head over here, another one on this side. So what we can do is fit a fastener into these. This is going to screw through, they're an open hole, and it's going to end up basically impacting on this section of the block, and basically we can then just wind those bolts down into these holes and this will lift the section of sump off here at the rear.
Now that we've got the sump out of the way, we've got a couple of little jobs to take care of. The first of those is we're going to be removing the factory oil pickup.
So here we've got our oil pickup. This obviously sits down in that lower section of sump that we already looked at and feeds up into the oil pump here. Another little tip to look for as well with engine problems with oiling is if the sump has been crushed. This happens a lot with lower cars. Basically it crushes down and it sits over this oil pickup so that the oil can't actually flow into the pickup.
It's something we do see quite a lot, and it can be a little bit hard to diagnose, and it can result in some pretty catastrophic bearing failures in the engine. So just watch out for that. If the sump, that lower section of sump pan, is looking a little bit beaten up and a little bit the worse for wear, it could end up giving you some other issues. As well as removing the oil pickup, we are also going to be removing the front cover off the engine because that houses the factory oil pump. With our dry sump system, we no longer need that factory oil pump. We're relying on an external 4-stage pump to draw oil out of the oil reservoir and then pump it through the engine. So at this point we're going to get that done. Not a lot more we can do though until our Ross components turn up from Australia. Alright, that brings you up to speed with our Toyota 86. Let's keep our fingers crossed that there's enough time to get that car finished before the start of our racing season. If you like that episode, give us a thumbs up. If you haven't subscribed already, make sure you do so. This way you won't miss out on any future episodes. And if you've got questions, ask them in the comments. In the next episode, we're getting back to where we should have been in this episode, and Brandon's going to take us for a tour of his KP60 Starlet.